Hey everybody, I thought I'd go ahead and put together a short video showing you how to solve problems dealing with Coulomb's law. So we're going to take on one of those problems here with the two balloons that you're seeing. So these two balloons were rubbed on somebody's head and they gained a certain amount of negative charge, and there's a separation between them and they're going to feel a force. Now, a first question you could ask is, well, what direction is the force that you're going to feel? Since both of them have the same sign, then they will feel the same kind of charge of sorts, and their force on them will be apart from one another. So these two balloons will actually be pushed apart from each other with a certain amount of force. And the question might be, well, how much? What is the force that they will feel? And that's what we're going to look for right now, is what is the force that these two balloons feel in opposite directions. So this whole thing is spared with this relationship that Coulomb figured out. And that relationship here is that the force between the two balloons is equal to some constant, right, times the amount of charge on the first balloon times the amount of charge on the second balloon divided by the distance between those two balloons squared. Now, in an example that I gave in class, I said, well, 1 Coulomb and a distance of 1 meter, which allowed it to be easy to solve this. But in reality, we typically work with things that are a lot smaller than that. In this particular case, I'm talking about things that are nano coulombs in size. So if they're nano coulombs, I'm going to have to work with scientific notation. And that is a bugger of a thing if you're not comfortable with it. But the more comfortable you get with scientific notation, the easier this problem becomes. So what I'm going to do is I'm going to go ahead and plug those things in order to help me out. The first thing to know is that this K is a constant, right? That K is Coulomb's constant specifically, and it is always the same number. And the number is 9 times 10 to the 9th. That's always the same number. It's a very large number. It is the scale factor for the relationship between the size of the charges, the distance, and the force itself. Now, the units after it are in Newton meters squared per Coulomb squared. It just happens to be the units for this, and you'll see why those are the units in just a moment. That's the K. Now I'm going to multiply K times this two charges times each other. And if I do that, let me go ahead and plug those in. I've got this negative 50 nano coulombs. So I'm going to do that. I'm going to put this in parentheses so I know what I'm talking about. Negative 50. And the nano coulombs, I'm going to go ahead and recognize that nano means times 10 to the negative 9th. You might have to go all the way back to the beginning of our stuff, your notes, to recognize where that is, or look it up if you need to. So 50 times 10 to the negative 9th. And now I'm working in coulombs. That nano means times 10 to the negative 9th. It is a billionth of a coulomb itself. I'm going to put my parenthesis back. And then the second one is the same, so I'm going to put it back in there again. Negative 50 times 10 to the negative 9th. Now I'm working in coulombs instead of nano coulombs, which is good. And then I'm going to divide this whole thing by the distance between them squared. Now, actually, let's put this in, instead of being in 1 millimeter, let's put this in as 1 centimeter. And the reason for that is I just kind of would say this is a reasonable distance between those two things. 1 millimeter is really quite tight, but even if you get it out at 1 centimeter, let's see what that would be. Now, centimeter is 1 times 10, because I'm going to put this into meters, to the negative 2 meters. Centa is times 10 to the negative 2. Again, this is something to look up or to go back to your original notes in the class. And now I'm working in meters. And the reason why I need to be in meters is because our unit over here on our constant is in meters and coulombs, so they have to be the right units in order to make this work. I'm going to put a parenthesis down here, and then I got to make sure I don't forget my square as I go. Now, at this point in time, I could actually turn right to a calculator and be able to solve this problem. The recognition here is that my unit's going to work out just fine to walk away with the units of force, because I've got newtons, that's my unit of force. My meters squared are actually going to cancel out with my meters that I eventually have to square. And then my coulombs squared cancel out with this coulombs times coulombs here. And so I'm left with nothing more than newtons. So that works out just fine. So my problem itself becomes this 9 times 10 to the ninth times negative 50, right? Times 10 to the negative ninth. And again, negative 50 times 10 to the negative ninth divided by 1 times 10 to the negative second squared. If I use a calculator, I'm going to go ahead and pull over a calculator in Google, because it turns out if you're here, too big. If I'm here in a Google window and I search now for scientific calculator, most of you will find that if you search for scientific calculator, it will pull up a beautiful little scientific calculator to be able to work. You can work with Desmos Scientific as well, but it is missing a button that I'm going to talk about here in just a moment. And the button that it's missing is this EXP button. EXP is a way of doing scientific notation nicely and quickly on a calculator. Other calculators, you might find that that button doesn't say EXP. It says just a capital letter E. The Texas Instruments calculators have an EE, both capital, but those are buttons that really mean times 10 to the, and you're going to see that in just a moment. So I'm going to start typing some things in to help me out. So I'm going to start out by putting just numbers, no units, into the calculator. So I'm going to put in a 9. That's where this is. And then I'm going to hit the EXP times 10 to the, and then I'm going to put in a ninth here. So this is 9 times 10 to the ninth. It doesn't look like it because it has the E, but that's a nice way that calculators work on this. And then I'm going to multiply this times, and I'm going to go ahead and do this negative 50 times 10 to the negative 9. So this is negative 50 times 10 to the negative ninth. And then I'm going to multiply that times the same, negative 50 times 10 to the negative ninth. And then I need to divide that. So I'm going to hit the division, but I need to square this thing. I got to make sure I'm squaring the right thing. So I'm going to put in a parenthesis to make sure I'm squaring the right thing here. I might not need to, but calculators sometimes get confused. And so I'm going to put in a 1 times 10 to the, and then I've got a negative 2. So negative 2. I'm going to close my parenthesis, and then I'm going to come over here to this xy, x to the y. That gives me my square. And so now I've got the entire problem. I've got 9 times 10 to the ninth times negative 50 times 10 to the negative ninth times negative 50 times 10 to the negative ninth divided by 1 times 10 to the negative second quantity squared. And when I hit equals, this solves the entire thing. So this step of translating into a calculator is often hard for students. And I'm hoping that it will be okay for you. So I hit equals, and what I get is 0.225, which is the answer I was seeking. That is the correct amount of force between these things. So my force in the end is equal to 0.225. And my units on this, the only thing I have left are newtons. So I've got 0.225 newtons. So the amount of repulsion between these two balloons is 0.225 newtons. Now at this point in the video, you can stop it and go forth and do your own work. But I'm going to continue for just a moment, and I'm going to solve this without a calculator. And the reason I'm doing this is to show you the power of exponents. So if you want to turn it off because you're a calculator fan, go ahead and turn it off. If you want to learn how to solve this with exponents and realize that exponents can be very powerful and why scientific notation exists, feel free to hang on. So I'm going to go ahead and erase this answer for a moment. And I'm going to hit an equals here, and I'm going to ignore the units for a moment, and I'm going to just focus on the exponents. So I'm going to write this 9 times 10 to the ninth times, and here's where the power of exponents comes in. You might have remembered that if I take x squared and I multiply x squared times x squared, what I walk away with is x to the fourth. If I take x squared and I multiply it times x to the fifth, I get x to the seventh. If I was to take x squared and multiply it by x to the 10th, I get x to the 12th. So what's the rule here? The rule is that when you multiply two things that have the same base, you add the exponents, and that's what I get here. So it turns out that I can do the exact same thing over here. The times 10 to the is the base side of that, and so I can just add the exponents. So what I'm going to get is negative 50 times negative 50, which is 2,500. 5 times 5 is 25, and then I have a couple zeros, and it's negative times negative, so it's a positive. And then I'm going to say times 10 to the, and then I'm going to add the exponents, which gets me to a negative 18. I'm going to divide this here by what's on the bottom. Now, if I take x squared and I square it, what do you do with the exponent? What's the rule here? X squared squared is x to the fourth. What if I was to do x squared and I cube it? What do I get here? In this particular case, I'm going to get x to the sixth. If I take x squared instead of I raise it to the power of 5, what do I get? I get 10. So what's the rule here? The answer is that I'm going to multiply these exponents to get there. So I added on the top, and I'm going to multiply on the bottom. So I would get 1 times 10 to the negative 4 on the bottom. All right, I'm getting closer. In order to do this next piece here, I'm going to go ahead and write in 9 times 10 to the 9th times 2,500 divided by 1. That is easy. 2,500 divided by 1 is just 2,500. When I get to my exponents over here now, it's divided. And if I get x to the sixth divided by x squared, what happens to my exponents now? What I walk away with is I walk away with x to the 4. What if this was x to the 6 divided by x cubed? What do I get then? I get x to the 3. Whatever I do here, I'm going to subtract my exponents to get to this other piece. So whenever I have a division, I subtract it to get to the other piece. In this case, negative 18 minus negative 4 gives me a negative 14. My last step in this problem is to multiply this 9 times 2,500, and 9 times 2,500 gives me this 2,500. You could do that on a calculator if you want to, or you could figure out that 25 times 9 is 225, and then I've got a couple extra zeros at the end of things as we go. So this is what I've got as a whole, and I'm going to go ahead and then take the exponents, and remember I add the exponents when I do it this way. So this is going to be times 10 to the, and if I add these two things, I get to the negative 5. I'm one step away, and if I wanted to simplify this, I have a decimal point here, and I can move my decimal point 5 to the left. If I did that 1, 2, 3, 4, 5, yep, which would give me 0.225, and that's my final answer in newtons. That's everything without a calculator. The more comfortable you get with exponents, the faster you can do this work, and the less I talked through the whole thing, so it took a while. But calculators can be your friends. You could solve things without calculators. It's up to you how you want to play it. I'm going to stop the video at this point, and hopefully that is a nice connection of how to do a problem dealing with scientific notation and Coulomb's law. All right, everybody, take care, and we'll see you in the next one. Adios.